So, hallo, guten Abend. Ich begrüße Sie herzlich zur heutigen Vorlesung und zum Distinguished Lecture und Gastvortrag von Professor Stefan Schall. Es ist eine große Freude für mich, hier ihn in Karlsruhe heute begrüßen zu dürfen. Einer der Wissenschaftler in der Robotik, die die Robotik und das Robotlearning pioniert haben, würde ich sagen. Und ich darf ein paar Worte zu Stefan, zu Professor Schall hier sagen. Er hat in München studiert, Maschinenbau und Artificial Intelligence, PhD in Artificial Intelligence, in künstliche Intelligenz. Dann war er Postdoc am MIT und dann Adjunct und Assistant Professor an mehreren Stellen, zum Beispiel Georgia Tech Institute of Technologie, Pennsylvania State University, und dann war er anschließend an mehreren Orten, wo man an der Schnittstelle zwischen Mensch und Maschine gearbeitet hat, vor allem die kognitive Informationsbearbeitung beim Menschen, beispielsweise am ETH in Japan, bevor er dann Professor an der UC am Computer Science, Neuroscience und Biomedical Engineering Professor geworden ist. 2011 hat er das Max-Planck-Institut für autonome Systeme in Deutschland gegründet. Und jetzt, wie man hier auf der Folie sieht, ist ein Direktor bei Google X. Ich will nicht viel zu seiner Arbeit erzählen. Der ist, wie ich bereits erwähnt habe, ein Pionier der Robotik unserer aktuellen Zeit, speziell der Robotlearning, von Imitationslernen, Dynamic Movement Primitives, was ihr in der Robotik 2 Vorlesung hier lernen werdet, aber viel mehr an der Schnittstelle zwischen Neuroscience, Motor Control und Robotik. Ich freue mich sehr, dich hier zu haben, und wir sind auch sehr gespannt auf deinen Vortrag. Herzlich willkommen.
Herzlichen Dank. Das war eine viel zu nette Einführung. Und ich wechsle dann einfach aufs Englische über, weil das ist wesentlich einfacher und für mich zumindest, als wenn ich technisch Deutsch rede und viel stottere. So I'll just simply switch. First of all, 1,000 thanks to Tamim to invite me here to give a talk. It was a lot of fun. I would like to tell you a little bit about some thoughts about robotics embedded in the research we've been doing for the last 10, 15 years, I would say. And it's pretty much about human-centered robotics, and it's about autonomous robots, which I'm interested in. Human-centered is very simple. We want robots amongst us at some point. We do not just want to deal with factory floors and very big, clunky, dangerous robots. It's a totally different discipline. Robots amongst us is still a topic which is out there. And there's no robot amongst you, from what I can tell. Which is weird, huh? After 30 years of robotics, still no robot which will just serve us coffee and cookies and Glühwein and whatever has to be done. Autonomous robots is clearly what we need if robots want to be amongst us at some point independently and can do things by themselves. So lots of people who contributed to this research, so I'm not going to go into detail. It's just too many people. It's a group effort. It is really me who just presents the work of many, many different people. And I'm really grateful for such great collaborators. So where to get started? So this is one of the spooky plots. Really boring, but really spooky. It shows you how our societies are going to develop. So let me see how the laser thingy works. Okay, here we go. Yes. Up there is what it used to be. So this is a population onion. You have plenty of young people, and then the older people get fewer and fewer the older they get. Unfortunately, this picture is changing. And it's changing towards something which looks like that. This is essentially 2100. This is, I think, 2050. But what's happening is there's suddenly way fewer young people and a much bigger proportion of older people. And so this is cool. That all means you guys are going to grow really old. This is lovely. So you will be all 80, 90, 100 years old or something like that. Unfortunately, you are not going to be just beautifully healthy. Your body still wears out and you will need some care and help in order to be still happy when you're 80, 90, or 100. And then that's the tricky part. There's not enough people left anymore who will be able to take care of those people who are older. And this is a problem. Okay, this is really not so far away. Okay, you've just 20, 30 years from now. This is 2050. This is a big problem. And this happens all over the world in all kind of high civilized countries. And everybody's worried about that and don't know exactly what to do. And Japan has that problem, I think, the most profound, and they're already shrinking significantly. I think Germany is predicted to shrink from 80 million people to 60 million people by this time, by 2050, unless something changes. So it's an interesting world, and the question is, what can robots do in this world? How can they help? And the first thing which comes to mind is, of course, that robots at some point can help in households, they can do elder care, they can help people where humans are not around. And this is kind of also a topic which is called independent living. Wouldn't it be nice if you can stay at home despite you don't function so well anymore with your body, but you don't have to go to a nursing home or do something like that? But we have many other problems. So space exploration, particularly for energy and other things in the future, epidemics, why the hell would we have human beings touch kind of clothing which people have been wearing who were sick and then dispose them and then they get sick themselves? So this could be done by robots at some point. We have natural catastrophes of all kinds these days. There's an interesting topic for robotics, which is actually prosthetics. How can you replace limbs which are missing with robotic devices such that the human pretty much functions as before? In general, there's the topic of kind of personal robotics. Robots which help you all and everywhere. In households, watching over your children, or just monitoring your children, guiding elderly people. Robots which teach people how to dance. Wouldn't it be nice, instead of going to dance class and basically trampling on the feet of your partner, you might actually start with a robot until the trampling part is over, and then you do it with a real partner. You can imagine all kinds of things. In another topic which is going to come, but this is more further down the road, is nanorobotics. You will swallow robots, and they will clean up inside of you. It will be really cool. And you know what the biggest problem of nanorobotics is? How to get them out. Swallowing is not the issue. But getting them out is really hard, which is a fascinating topic. Okay, so tons of interesting topics in the world. So we've been looking at robotics in a little bit broader way over the last years. So we think as robots as perception, action, learning systems. And this is really towards autonomous robots. A robot has to perceive, it has to be act, and it has to be able to learn. This is kind of the underlying idea in little systems, little robotic systems, bigger robotic systems, very big robotic systems. You need those cycles to be autonomous. Perceive, act, learn, get better, fix things if they don't work. And from that point of view, you can think about all autonomous systems like they are perception, action, learning systems, no matter on which scale. From my point of view, these are all intelligent systems. I do not going to start any discussion about what intelligence is. I think if you can do that, like a little bee, a little fly, I think you have plenty of intelligence. And we are nowhere in our artificial intelligence systems with these kind of things. Now, when it comes to real research, it's nice to break these things down. So perception, action, learning system, so we can put this into some block diagrams, which people in control and robotics like usually. And then we have here the robot and its environment. Very important, the environment is really important, not just the robot. Interacting with the world is what makes life interesting, not just floating in space and not touching anything. All of you interact all the time. You touch stuff, you sit on stuff, you lean backward, you scratch behind your ear. You just interact all the time. And that is actually the interesting and exciting part of robotics. So environments matter. And then you have some kind of sensor processing, you have action generation, you have noise processes, you have learning systems, just a generic diagram. And from a research point of view, what is nice is then somehow take this into a more formal framework that you can, at some point, write algorithms and program these algorithms. And then you go and create models and equations. So this is, for instance, just a differential equation which says, OK, we are modeling the robot and its environment. I have no idea what goes into these functions, except there's some state vector, there's some controls, there might be some time dependencies and noise sources. And that's pretty much all. And for kind of perception, I can do the same thing. There's some state, some controls, some time, some noise sources. And I have to basically figure out what I can observe in this world. Now, these equations are meaningless insofar that they're just sitting there. The interesting thing of research is essentially how to fill them up with appropriate, more detailed subroutines, algorithms, whatever comes to mind. So the computer vision people always hate me when I say this. But I absorb all computer vision in there. That's it, no problem. And in some sense, it's actually cool. In the old days, computer vision would create perception pipelines over multiple computers and very complicated things. Now, these days, actually, that might be just a deep neural network. And it literally does it all. So my story, which I always said, oh, this is much more structured, is now kind of reversing. And say, hey, it may not be structured at all. People just learn it directly. And that may work or may not work in some cases or not. So our research over the years basically was also a little bit more structured. We've been working on robotics, a little bit on theory and algorithms, and a little bit on behavioral studies, just getting inspiration from neuroscience. And again, when it comes to motor control or perception, humans and animals are just so superior that something seems to be working in these brains. I don't know exactly how it works, but it works really well. And we are not capable of doing the same in artificial systems so far. And then we basically talked about, in our research, about various components, how to structure this. So for instance, planning, modular planning, this means thinking about representation, teaching and imitation, reinforcement learning, autonomous self-improvement, essentially trial and error learning, how to interact with the environment, how to react to the environment. Not everything is just heavy-duty computations. All of you react all the time very quickly to certain things without, so to speak, thinking too much. You just react. So they are reflexes and things like that. And I think it's a very important component of robotics. There's control, learning control. And in the end, there's the interplay between perception and action in the entire perceptual system, which has to come in there. And in the research of my research groups, basically, I can show you a little bit of pictures what we've been doing there. And this is just to give you a glance, just ideas, not that will be any details. And I'll show you some more details right afterwards, slightly in a different context. So what we've been doing is we did motion planning with a tractor landscape in the part. We did kind of potential field planning systems. We did kind of learning of state machines and decision-making in manipulation, a little bit of functional magnetic imaging to figure out how motor control works in the brain, non-parametric learning of grasping with so-called templates, reinforcement learning, how to learn complete motor skills, Bayesian optimization techniques to tune parameters of controllers automatically, obstacle avoidance, inverse reinforcement learning, that means how to extract a cost function from observed behavior, grasping, manipulation, and learning how to do that, complicated manipulation tasks like manipulating tools. We have been working on biped locomotion, machine learning, balance controllers of all kinds, and complicated rough terrain planning with multi-contacts for a robot. Perceptual things, one important thing is really to track what's happening in the world. So perceptual tracking systems, new filters, databases of how to grasp and evaluate objects from perceptual input, whatever, manipulation of kind of assembly tasks, and in the end, non-parametric learning for computer vision. So that was super fast. This is like 8-9 years of research lumped together. But you get some pictures, and it was actually ordered a little bit along that circles that it went from more planning, representation, to learning, to control, and in the end to perception. Now, I just want to look at this now, the research topics we've been doing from a slightly different angle. And I want to look at it much more from the idea of human-centered robotics. And so what are good applications? Where would you like to start with human-centered robotics? Let's assume I give you $1 billion. and you can create a research institute, and I tell you, do human-centered robotics. What would you be doing? How do you pick your challenges, your research topics? What is interesting? What applications would you use? Well, walking the dogs, maybe. People will most likely not give you money afterwards. Helping someone who had a stroke problem, absolutely. Helping someone in a home, absolutely okay. Hugging children, fine. If you volunteer your children, go for it. Taking care of the trash, that might actually be useful since there's a lot of trash in the world. So fine, I'm just getting around a little. In general, the topic of personal robotics, I think, becomes interesting again. So let's just look at some of the research topics you might want to think about, and I tell you a little bit what we've been thinking about. And so what do we have? Here's kind of criteria and issues which we learned over the past matter. So one thing is, for instance, simplicity and stereotypic motion, and I will tell you a little bit about that in a second. I just flash them up and I come back to them and talk more about them. Reactive motion and sensor-rich and adaptive processing. Confidence, self-awareness, that you need to know what you're doing, you need to monitor what you're doing, and you need to be failure safe and things like that. Learning, calibration, lifelong learning, learning forever. Nobody in robotics has an algorithm which runs forever. Actually, most machine learning people cannot leave their learning algorithms run for the rest of their life. They always unlearn at some point. So lifelong learning is a super cool topic, I believe. Perception, multimodal, robustness, whether you basically process things in the cloud at some point for heavy computing, or whether you can do it on board. There's a lot of data-driven robotics these days, cloud computing, and how to collect rich data sets which can actually take advantage of some of these deep neural networks. Hardware is a huge topic, and how to create safe hardware, whether it's mobile or not, how complicated it is. And in the end, basically, you go back a little bit to the topics where you want to apply things like physical assistance for people, or non-physical assistance. You don't always have to touch things. You can also just be fun. You just go in front of a person and do hoo, 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 ha, 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 and then the person smiles and takes the pills. And that's what you wanted. So there's lots of ways how you can actually also influence people by not touching anything in the world, which is actually a topic of what is called socially assistive robotics. Quite important. All right. Let me get into some of the details and tell you what I mean with that. So for a long time, we've been working on something which I consider really super simple. The idea how to plan motion in a way that I don't have to create a new representation every time for every motion I want to do. Whether I want to chop vegetables, or whether I want to do locomotion, or I want to reach and grasp, or I want to manipulate an object in a different way. And so it's literally now 15 years ago that we started to work with representations of motion planning, which are differential equations which look like that. And if you look at them carefully, they're actually spring mass damper systems, and have a little bit of a function approximation machine learning term in there. And what it allows you to do is essentially, it allows you to define, the goal of what you try to do in a skill is an attractor. And that might be a attractor which is basically reaching for a point, or basically having a grasp pose, or it could be also locomotion. And if you model these things, then what you get is something really nice. You basically can start in many, many different ways. You will always end up in the same goal state. This is shown as a typical kind of little picture of a landscape where everybody rolls down into a valley. Let me show you how this actually works in robotics, which is much nicer. So this is actually a KIT student, Peter Pastor. Tamim is nodding. Many years ago, Peter basically was an exchange student and came to USC in Los Angeles. And he worked essentially on those motion planning systems. And what you see here is essentially what we call a motion primitive, or a dynamic primitive, which has as parameters a goal state and also a speed parameter. And then no matter where it starts, it will always use the same primitive to get to the right spot. You don't have to replan, you don't have to do anything. And so it is basically some basic grasping motion, a transport motion, which was taught by demonstration, and then it can be reused in many different scenarios. And I really like this. It's basically, these things code a family of movements. It's not just one. It is basically a lot of things which are self-similar, which serve the same purpose, just in slightly different ways in the workspace. And So that was the early version of pouring. I think there was a kink in one transition, and then a little bit later, which you see down there, was done much more nicely. Again, one motion primitive pours all and everywhere. It doesn't matter where you put the glass. We used color vision at this time, so that's why you have these bright colors on some of the objects. So this is this is the spirit which I would really like to have. I would love to have a library of those kind of simple motions, which I then can use and adapt to many, many different scenarios. What is important actually about this primitive stuff is it creates also, it's really simple to set up. It's also something which is very predictable and stereotypic. So all the motions look self-similar. So I actually know what to predict when I'm doing something. So why do I emphasize that? The competitor in the room, so to speak, towards these kind of primitive approaches is essentially general optimization of trajectories to get from a point A to a point B. And these are just generic optimizers, which basically you give them a cost function, a start and an end point, and they will somehow optimize something. Now, anybody who's ever worked with optimization will figure one interesting thing out. A small little change in initial conditions may make the optimizer create a very different path how it realizes to get to the goal. All is valid. But one time you may be going to the goal like this, the next time you do like this. Now I don't want that. That weird exaggerated movement I don't want. I want to know what I'm dealing with, what am I getting out. And ideally I want to basically be very stereotypic and use the same things again and again. Why do I care about this? If I do this, I can predict what's happening. I will not be surprised. This means if I do a motion multiple times and I always use the same kind of motion, I can collect statistics about my movement. That means I know how things should actually look like, what position traces I should have, or what I should be feeling, or what I should be seeing. It should always be the same. And if you have that predicting ability, then you can actually do a couple of other things, which I'll show you in a second. So prediction, I think, is super important and a topic which is used way too little in robotics. Let me go to the next point, which is reactive, adaptive, and sensor-rich. And now I'm going back actually to my idea. So I like to do motion planning with dynamical systems. So it doesn't really matter how you formulate them. In the end, you could graph them. So this is a very simple graphical model over time, which simply says, I'm currently in state X. I would like to be in state X desired. So the two things together basically combined and create some kind of a control signal, which then goes to the robot, and I go to the next state. And then I have a next desired state. So it's a typical succession of robot state, desired state, motor command, going to the next one. So boring. What is interesting is actually, this is kind of a very motor-centric view of the world. It just talks about robot state and robot commands. But there's much more out there. There's lots of sensing, increasingly more sensing what we can put on robots, whether it's touch sensors, acoustic sensors, that means microphones, or of course visual sensors all on everywhere, rangefinders. That means you can actually say at every time slice, you also get sensory data. And now I come back to this idea, if I do stereotypical movement, the sensory data which I'm experiencing should also be stereotypical. It should always feel and look the same. Good. So that means after I learn the movement and I do it a couple of times, I actually know what my sensory expectations should be. And then the interesting thing is, well, if I'm now executing the movement one more time, and the green things are now basically my current sensations, and there's a difference relative to them what I am expecting, I have an error. And I can use this error, for instance, to correct my motor commands. Now, all of you are expert in exactly that. So if you walk on the pavement and you don't pay attention, there's a hole in front of you, okay? You are not going to step into this hole all the way. You already notice a little bit before you step into the hole that, oh, something is wrong, and then you step aside. You were predicting what you should be feeling when your foot touches the ground and when it's happening. And if there's a hole, you do something. You will not blindly fall into the hole. So we are predicting, we humans predict all the time, everything. And reactive, something doesn't feel or does the right thing, you will react to it and do something. And we would love to put this a little bit into robotics. So we basically think about motion, or actually motion skills by now, as something which is just the typical motor representation, but it's augmented with all kinds of sensory information, which we associate with every moment of time and basically create predictions. And if you do this, and you can make this even a little bit bigger, you can have some context which belongs to a particular motion, and you can augment it with cost function, which we would learn with inverse reinforcement learning. I'm not going to talk about this a lot. But then you could suddenly, a bigger picture is not just motor, it's perception and motor, and sensory and motor representation, which you can use in order to make decisions later on. And I will tell you actually in a little bit what you can do. For instance, you can basically correct if something doesn't do right. You can basically abort behaviors, or you can switch behaviors. I will show you a little bit of all of those things. So we call these things associative skill memories. Well, there might be nicer names, but it's just a relatively useful name. So here's an example. So this is, again, Peter Pastor, the KIT person, teaching a robot how to grasp the flashlight. So the flashlight is sitting on the table. There's no vision at this moment. It's known where the flashlight should be. We assume we have already done the perceptual part. And the robot basically does this a couple of times, collects data, knows how it feels when it approaches, and knows how it feels when it touches the flashlight, and how a successful grasp looks like. All right, and then you basically create a little bit of a controller. And this robot, which you see there, has actually all kinds of force sensors in the fingertips, in the wrist. And you can put all of these together into a bigger picture of motor and sensation, and then create control systems which have force feedback on a low level, and they also basically feedback signals into the planning level, which is our motor primitives. And with these kind of feedback loops, you can do amazing corrections if something is not right. So what's now happening is the same picture as before. The green spot is where the flashlight is thought to be, but it was displaced. And this is kind of the controller I showed you on the previous slide, which basically notices when it touches the flashlight, that doesn't feel right, and then corrects and wraps itself properly around the flashlight. So it's correcting for about a 13 centimeters error in perception, which is huge. And again, all of you know how to do this, okay? You get up in the night, 1 o'clock, you need to go to the bathroom, you fumble around, find the light switch. This kind of fumbling you do, if it's not in the right space, you correct. You don't have to see anything. You don't get your eyes open anyway at this time. So you just do everything with tactile perception. And it's amazing what you can actually do if you just know what to expect from your sensing systems. Okay, so this is a little bit about reactive and adaptive processing of signals. And I think these reactive and adaptive things are really important. Let me share you a little bit more about confidence and self-awareness and what you can do with this. And this is actually continuing the picture of these associative skill memories. And here's a different way of drawing them. So this is now time in the horizontal axis. And these are just different sensory traces in the vertical axis. The intensities have been normalized so that it's a nicer picture. So in some sense, what you're seeing is, okay, this is a motor skill from 0 to whatever, so and so many seconds. And these are all the sensory traces which you have been experiencing, and for a particular skill, and that is kind of an image of the skill. It's a little bit silly to draw it this way. It is just my absolute envy towards computer vision people that they have images. It is such a nice and simple representation. It's just a rectangular with intensities. We don't have this in robotics. This here is not an image properly. Each of these data traces is actually its own dimension. That would be a whatever 30-dimensional space, which I cannot draw at all. But it's still something which gives you an idea of what you're dealing with. So now take one time slice here. This is essentially, at this moment of time, a perceptual motor signature of that skill, what is happening. Now, why not use it as a vector and start processing with machine learning in it and try to predict what happens next, try to predict if some failure happens, try to get much more data-driven than analytical. So let me show you for a second what you can do with this. So if you take now these sensory traces and you collect statistics over them over time, and this is when the robot learns with reinforcement learning a silly skill of tilting a cube. And the cube is equipped actually with an IMU, so there's a measure of success whether this works. There's a PR2 robot which has tactile sensors, actually a whole bunch of tactile sensors in the fingertips, and they were simultaneously recorded. This is just showing you that the task is actually not that easy. This is some humans which tried as well. What is nice about, after you learned this skill, just to re-emphasize what I said before, you can look at your data traces. These are now the fingertip sensors, and look how they look over time. And you can also draw them in green when this was a successful trial, or in red when it was an unsuccessful trial. So you actually see there's a big difference between successful and unsuccessful trials. And if you have that knowledge about the statistics of that skill, you can look at training data. That means you try to do the skill again. This has not been used to basically train up these simple statistics of the associative skill memories. And again, you can see that when something goes wrong, the red traces here go out of the confidence intervals of the green traces. Now, what is really nice is, look at this here. Halfway before I finish the task, I know it's going wrong. I don't have to execute it. So I don't have to fall into the hole which is in front of me in the pavement. I can actually figure that out way before that something goes wrong and can abort or switch or do something else. And this is actually in this follow-up project that was actually right now part of Daniel Coupler's defense. So here the idea was now using really machine learning classifiers which basically try to make a prediction at every moment in time of a movement skill, whether to continue, to switch, or to stop. And it uses this kind of representation from these associative skill memories, that big vector of all signals over time, to just automatically learn these decisions. And what was nice is actually it automatically learned how to switch to different behaviors. So the robot was taught a couple of primitive behaviors before, but it automatically learned how to switch between them until a skill was fulfilled. And I just skip that and just show you a video which is more fun. So this is actually now a robot doing bimanual manipulation, trying to screw a cap on a bottle. And it learned the individual skills from demonstration before with sensory statistics. But then it learned completely by itself how to switch back and forth based on these classifiers, which are essentially all kind of Bayesian classifier-like things. And what you will see over time, this becomes actually, so what you see on this side is just basically the confidence in certain data traces which come and when to switch automatically. The robot got actually all kinds of sensory signals in these associative skill memories, including acoustic signals, which were completely irrelevant in this particular task. But you will actually see in a moment that you can now start to perturb the robot, and it will then automatically switch into recovery behaviors and just continue until it finally gets the job done. So all our robots are in torque control mode. They're very compliant. You can very easily push them around just with a fingertip, as you can see here. I think there will be some clapping at some point. And if you bother the robot too much, it will just reset and go into recovery behavior and just redo the task until it's finally done. So this is really cool. This is really robust behavior for a fairly complicated manipulation task. Okay, let me just move forward. Just another example of that was how to learn to automatically grasp objects. This is pretty much the main issue here is that there are these special green fingertips. These are special tactile sensors which give you sensory processing very similar to what your human fingertips can do. They can feel pressure, forces, heat. They notice when things are slipping. And you can use that to actually learn over time how to grasp and re-grasp objects automatically. Let me emphasize one little thing. This red pot here has nothing to do with the task. It's an automatic reset mechanism for that cylindrical box, and is allowed that the robot could keep on learning and create data as much as it wanted. What is nice, essentially, after a while, the robot basically learns how to grasp an object. If it doesn't grasp it right, it will re-grasp the object, and then it will be happy. And all of this is, again, triggered through these kind of sensory signatures from all sensors which the robot has available. OK, let me just move on a little bit. OK, so this was a little bit about self-awareness, failure prediction, recovery, confidence, and issues like that. Let me talk a little bit about learning and recalibration. So we've been doing a fair amount of machine learning for robotics over the last 20 years. And one of the relatively older things from 20 years back was actually to learn robot controllers or robot models with very, very fast learning techniques. And here's this one thing which is completely forgotten at this moment of time. There's two kinds of learning. Okay, there's one kind of learning where I give you a bag of data and you process the hell out of it and you give me some trained model back. The other thing is incremental learning. You learn really, really on the job very fast. Most networks right now would die a horrible death as you did this because they cannot balance the data appropriately. But there are algorithms which can learn. And actually, you can create learning algorithms which learn so fast that you actually never need representative data from the entire world. You just basically, while you're moving, you move into an area which you have not seen data. You learn within a fraction of a second some local simple models, and you can use them for control. I will show you this in a second, which is actually real fun. We've been working a fair amount on reinforcement learning algorithms. This is actually really cool, but maybe I don't go too much into this. This is what is called path integral reinforcement learning. It's, again, something very actually funny. We worked really hard here to create a reinforcement learning algorithm which does not require derivatives at all in order to learn. And now the entire world wants to have stochastic derivatives in deep learning. So we hate derivatives. Derivatives are miserable. Because if you hit something, a discontinuity, the derivatives look very terrible. So robots interacting with the world, if you optimize through these things, you get discontinuities. And they are not nice for derivative taking. We worked a little bit on deep learning methods in the context of reinforcement learning and some meta-learning approaches, how to basically make things faster. Let me just show you some minimal examples. OK, this comes twice. Interesting. Just reinforcement learning, in case people don't know this. Reinforcement learning is just learning from rewards. That means nobody tells you exactly what to do. You do something, it works or it doesn't work. If it works, you're happy. If it doesn't work, you're unhappy. And the approach basically goes around that you need to somehow create a cost function, and then you have some kind of a control system which has open parameters. This is actually our motor primitives again, and we just use this B thing here as open parameters. And then you try to optimize these parameters relative with respect to the cost function, which is essentially a gradient descent technique in most cases. So this is kind of the most generic setup how to do reinforcement learning. And yeah, I'm not going to go through this. You can make this actually with a little bit of math a really cool approach. Which works then without derivatives and other things. This is what it looks like as math, and nobody likes that. So let's get rid of it. This is much easier to understand. So this is time, and that's a position, just a 1 degree of freedom system. So all what I'm doing is I do multiple trials to get to this point up here, and I do this with a little bit noise injected, OK? And these are the velocity traces. Again, velocity, vertical, horizontal is time. You see the variation due to noise much stronger there. And then you create an algorithm which basically tries to figure out what is the best to do, how to optimize the execution of this trajectory. And what you do is essentially you have a cost function, and you add up rewards along the trajectory. And the interesting thing is, when you add up these rewards along the trajectory and run them through an exponential function like shown here with a scaling parameter, you can think of it as becoming a weight. And it's actually a strictly positive weight. And then from every trajectory at every moment of time, you can actually create a weight which represents how good this trajectory was. And if you want to do an optimal trajectory, you just do a weighted average of all the motor commands of all the trajectories at this point and combine them. So surprisingly, This super simple equation down there is the outcome of that weird messy stuff before, which was officially stochastic optimal control with the Hamilton-Jacobi-Bellman equation. And this is really cool. And let me just show you what you can do with that. Actually, I want to show you two things. This on the top, I have to go back. Let me just prepare you for that. So this is actually, the first picture is about learning very, very fast, like in fractions of a second models, in this particular case, of the inverse kinematics of this humanoid robot. And here's two reinforcement learning algorithms, one with deep learning, one without deep learning, which uses this, what we call path integral reinforcement learning. But why I have to stop here, the robot has no knowledge when it starts how to try to reach for that red ball. But you will see it learns literally within a second or two how to get there. And that's kind of a different way of learning. I just have to go through this again, just a second. Okay, robot learns, and that's how long it takes to learn. So this is really cool. I so much like that kind of learning, where you learn literally on the fly as quickly as you can. And you can run relatively complicated models, but they don't have the same power as, for instance, deep learning has. Deep learning can learn more complicated things. In the other videos, you see actually here a robot learning how to gently grasp a pen from a table, which is a force control task, where it basically learns how to minimize forces but still have a stable grasp. This is done with reinforcement learning. The same reinforcement learning algorithms inserted here in a deep learning approach, where a robot learns how to open and close a door. No, not close, I think only open a door. And the reinforcement learning is actually used to generate data for a deep learning network, which then generalizes over a larger workspace. Okay, and I think in the end this Dozenten video has learned it and can do the task nicely and repeatably. It's actually, you always have to do everything relative to the robot hand you have. This is not such a dexterous robot hand to pick up things like that. All right. So this was a little bit about learning ideas. Perceptual things. There's actually two kinds of what is interesting about robots in perception. So there's one thing, you can do what is called perception for action. That means you perceive the world, and then what you perceive should trigger the appropriate motion. So for instance, a cup affords that I can grasp it. This is often discussed under the word affordances. That means whatever you see in this world, you could actually label it in how you can manipulate it and how you can act on it, not just that it exists. And that is really what matters for your survival. You would never try to sit down on a tiny, minuscule toy chair. You would only sit down on proper chairs. You know, the toy chair is a toy, so that allows you to grasp it. The big chair is for sitting on, so you basically turn around and sit on it. But there's also another way of perception on action. This is essentially where you use action in order to perceive better. And this is actually currently discussed under the word of interactive perception, where you literally use your robot to move around, to touch things, to manipulate things until you have confidence in what you've been perceiving. And I think both topics are really cool to do research on. We've done a little bit on this, but there should be much more to be done. Just some examples of what we've been working on. So one topic was basically try to track as many objects in your workspace as you can do. So these were some new kind of particle filter-like methods, which are very, very efficient and can basically observe the entire scene in front of you, not just one object. You can think of that. This is very similar to what autonomous driving people have to do. You cannot just watch one pedestrian and just run over all the other ones. You need to look at all of them at the same time and track them. And this was kind of inserting ideas like that and other research components into complete perception action system where really there was real-time perception working all the time and informing the action system, correcting if something was right or wrong, and making sure that there's always a closed loop of a system. This is relatively a huge amount of work to create a complete system which has all kinds of 3D perception, color perception, tactile perception, learning components, self-calibration to make it work. So let me just move on. Let me talk a little bit about data-driven cloud computing, etc. And I'm not going to really talk in detail about that, but what we noticed over the last years essentially is that we have people in our research groups which have essentially different preferences. Let it put it this way. Some people like heavy data-driven approaches, which is deep learning. Some people love model-based approaches. That means they write equations and manipulate the equations to create controllers. This is the clean way from a robotics point of view, except we don't always have decent models about all and everything. So we have to go data-driven at some point. And I think the interesting question is, what is the good middle ground? How much modeling and how much data-driven should we use? The same, there's another way of basically planning everything with optimal control methods versus reacting to the world in a simple way as what you see with the flashlight manipulation. All of these things somehow belong together, and there should be some middle ground where they all come together and you use the right thing at the right moment for all and everything. There's just one thing. You cannot just do everything data-driven in robotics. It may work in vision to some extent, in natural language processing, but if robots have physics to obey, and you cannot, if you learn just purely from data, what we've noticed many times, you basically learn something which is physically incorrect. And then you tell the robot to do something physically incorrect. So my favorite example is I used to use learning algorithms to learn basically model identification of rigid body dynamics without details. What you learn is partially inertia matrices. If you remember what inertia matrices are, they are little 3x3 matrices, and they have a certain property. They should be positive definite. That's a mathematical property, which is, that's what physics does to you. It wants it. If you don't make it positive definite, they are not inertia matrices anymore. They have nothing to do with physics. But my learning stuff learned happily all kinds of not positive definite matrices, and I put them in a control algorithm and exploded. And then you need to figure out what the hell was going on. So physics is actually something really cool, and inserting physics into learning algorithms and constraining them through physical insights is actually something which is really helpful. One other thing which we really love to emphasize is the idea that people should all know about perception, action, and learning. We don't want just the computer vision guys and the robotics guys and the ML guys, and none of them has an idea of what the problems of the other groups are. You need people who really start to have at least decent knowledge in all three areas so that you understand that machine learning for a closed loop perception action system is a very different beast than machine learning from a bag of data about web pages. It behaves differently, and you use different techniques for these kind of things. All right, let me just get slowly to an end. I just wanted to say something about hardware. So this is all the hardware which we've been working with over the years. There's one common theme to all these robots. They're way too complicated. They're way too brittle. They're way too maintenance intense. So at some point, it would be really nice to have very robust robots which do not have this too high complexities. Well, these are research robots. It's a hydraulic robot which has all its idiosyncrasies to the extreme. This is a cable-driven robot which just needs to be recalibrated all the time. And people build much better robots by now. But hardware is an issue, and what you will notice if you ever work with real robots, there's a fair amount of work you do to work around the stuff of the robot which doesn't work right. And it's quite annoying. So it would be really nice at some point if we had some standard robots which are simple and super reliable. And then there's certain robots on the market which seem to move towards that. Let me come to the end. So I just wanted to show you a little bit all the thoughts which go into creating at some point human-centered robots, autonomous robots, all the components you should think about. And this is obviously not all the components. This is just my subset of components which I like the most. So it's a pretty big spectrum which you have to bring together to make these things work and become reliable autonomous robots, and we are not really there so far. On the other hand, we don't have so much time. Okay, we were sleeping the last 20, 30 years in robotics. We have not created robots which are amongst us and can help us. But that population onion, this is coming in the next 20, 30 years. So it's really time that we move forward and figure out how to do robotics properly. Thank you very much.
Ja, vielen Dank für den, thank you very much for the nice presentation.
Was immer welche
So,
Sprache.
now we have time for questions. Are there any, or who want to start? Okay. Do you have another mic here? Fabian?
You can try shouting.
Yeah, you can try.
Yes, I can.
Professor, could you, if you could you go back to the slides when you were talking about the difference between deep learning and the other way of learning, learn on the go? There's a equation for the reward system. So the one before, I believe, is the one before.
24. Oh. Yeah.
Like the reward, the equation for the no, this one, yeah.
Oops. Not this. No.
The R function, the reward thing, when you're optimizing the.
You mean the graph?
There are like two graphs. Yeah, I believe in the next one.
This one?
Yeah, this one.
Okay.
Yeah, Professor, I'm wondering, what is the reward here? I mean, you said it's basically like a weight function. Could you elaborate a bit more on that?
So the reward in this particular case, well, first of all, the reward can be anything. It's usually a mixture of an arbitrary function which depends on state, and it has to be a quadratic function which depends on the commands. Now, what most people use is usually, you always penalize to some extent the commands they're using, so you don't basically use excessively large commands. When it comes to state-based rewards, the simplest thing is you want, for instance, the distance to your goal minimized. That's the simplest thing. But you can do something much more complicated. You can think about, so if you want to bounce a tennis ball on a tennis racket, you create much more complicated reward functions about you want a constant height of the ball and things like that, and low variance, and you can create very complicated reward functions. So this is essentially where the world gets quickly into what is called inverse reinforcement learning. Certain reward functions are very simple, but then comes something which becomes completely arbitrarily engineered, and you can tune parameters for the rest of your life.
Other questions? Yeah.
You mentioned the physically constrained machine learning. You gave the example with the inertia matrix, which I found really interesting. Do you have other examples, and how could you elaborate on this topic?
Yes, I can a little bit. There's various people who basically try to think about this. So what have people been doing in the past? One simple thing was, for instance, for learning dynamics models, people used actually as internal start as bias, essentially, an analytical dynamics model, and then just learned from data the error relative to the analytical dynamics model. So basically, they learn for the unmodeled effects. It's a little bit of a physical constraining. It's not proper. People in deep learning have started, I think Dieter Fox's group for a couple of months or whatever ago had a paper where they basically tried to learn transformation of objects in space with deep learning, but then they made sure that in the last step, it's projected that it's a proper affine transformation. So it's not some arbitrary transformation, which is maybe the thing stretches and does weird things, which is not realizable. So people think about at which layer they can insert some kind of physical constraints, which says, you cannot do this anymore since it makes no sense. How to do it in a principled way, I think people are guessing at this moment. In the end, you need to project the solution of an arbitrary system down to the physical, quote-unquote, manifold. But that's easy said. It doesn't mean so much if you don't know how to realize it for the problem you care about. So for instance, when it comes to learning for control with deep learning, these networks output all kinds of garbage. Like they create torques which are way too high, discontinuities in torques which are terrible. All of this, please do not put this on a robot. That would be bad. Works fine in simulations. Simulations are very forgiving.
Hello, Professor. I have a question regarding dynamic movement primitive, because I'm working on that. And one thing bothered me a lot. So because I have read a lot of papers regarding the research using neural network as policy. Do you think in the future the DMPs, these shallow structured policies, will be replaced by these deep architectures?
This is a very good question, and yeah, and I actually don't know. And the thing is that with deep learning currently, people learn the most trivial things which we know in robotics all the time again. And they need, I don't know how many millions or terabytes of data to do that. It's really stupid. Okay, I can do a point-to-point movement really nicely with a primitive representation or spline representation. I don't need deep learning for that. So I'm not sure whether we should try. It would be interesting. So what we've been thinking about, for instance, is that we use our motion primitives. But what we do now, for instance, if it comes to modifying them for obstacle avoidance or for force control, we learn neural network modifier terms which are additive to the primitive equations. And this way we get a little bit the best of all. We basically have our normal structure, which is reliable when there is nothing weird. But then we have the modifier, which gets turned on if something unexpected happens in the world. And that became partially deep learning networks. So there might be a way to combine them. But I have no idea what's going to survive. I think it's totally out there.
OK, other questions or comments? OK, this seems not the case. So I have a question. What would you recommend actually? So what future roboticists should know?
What
future roboticists? You know, these are the students who are interested in
what
robotics.
They should know?
What they should learn actually, based on your 20, 30 years experience.
OK, what should they be learning? That's very easy. Well, they need to learn control, modeling, physics, machine learning, computer vision. Actually, a little bit of cognitive science is really helpful, neuromotor control. At some point, if you want to do social robotics, you need definitely cognitive sciences. It really depends what you want to do, but I think in the end, people should know about physics. If you work with a physical system and you don't understand you work with a physical system, it's really bad. So some appreciation that there's differential equations and that there's physics and it has its own laws, I think is super important. And then basically adding specialty things which you care about, like machine learning. Well, machine learning is super cool since you get a good job this way. It's very popular. Computer vision or some kind of perceptual processing is helpful. And all these things become easier, I think, as tools to use. You do not need to study all and everything to the last level of detail. So, but a little bit of all of these topics these days, I think, is really valuable. And work with a real robot, not just with a simulator. Simulators are cheating.
OK, so Lagrange is important, right? And Lagrange is important.
Lagrange is,
and
the Newton guy and all of those people, yes.
OK. Yeah, thank you very much. Let's thank Professor Stefan Schall again, and thanks for everybody for coming. Yeah, thank you. Thank you. Super. Super.